Oh, hi. So our next talk will be given by Piotr Przytycki. So he's a faculty in Department of Mathematics and Statistics of McGill University. He'll be speaking on Coxeter groups are biometric. So over to you.
Thank you for the invitation. Is the microphone working? Yes, raise your hands. Thanks. So the title of this mini course is that Coxeter groups are biautomatic, and it is joint work with Damian Osajda. So hopefully by the end of the mini course, I will convince you that Coxeter groups are biautomatic. But in order for this to happen, I have to introduce these notions. So today's course will be about biautomaticity of groups. And to start discussing biautomaticity, I need to introduce at least one definition of a regular language. So here is where we start. We will work with a finite set of letters, an alphabet. So let A be a finite set whose elements we will call letters. And then a word over this alphabet A is just a finite sequence. It's a finite sequence of letters, possibly a sequence of length 0, so possibly it's an empty word. Possibly empty, and an empty word we will denote by epsilon. And now a language is a set of words. So a language over A is a subset. This one can be infinite of the set of all words over A, and the set of all words will be denoted A star. Questions? So now we will discuss automata and their languages. So definition of a finite state automaton over the alphabet A is the following. And you will notice, if you know the textbook edited by Epstein, word processing in groups, that this is, in fact, a definition of a non-deterministic finite state automaton. So what is this automaton? It is a directed graph, a finite directed graph. Let's call this graph gamma. And we will call its vertices the states of the automaton. So with vertex set that we usually denote gamma 0, called the set of the states of the automaton. And edges, so not only it's a directed graph, but its edges are labeled. And we want the labels to be either elements of the alphabet or the empty word. So labeled by the elements in A union the empty word. And we also distinguish a start state and maybe more than one accept states. we usually denote the set of the accept states by Y. It's a subset of gamma 0. And then once you have this directed graph labeled by the letters with a start state and accept states, we can speak about the language of this automaton. So the language of such an automaton is the set of all words labeling directed paths from the start state to one of the states in Y. So let's do an example because it's a long definition. Let's look at the graph where here I have my start state. And then I will have 4 sort of intermediate states and the next state here. Then I will have paths from the start state to this state labeled by all possible words of length 2. So 0, 0, 0, 1, 1, 0, 1, 1. And then let's draw another arrow going back here, labeled by epsilon. And to finish the definition of an automaton, I need to say what is the set of accept states. So let's say that Y is just the single state, this start state. So now if I'm supposed to study the language of this automaton, I need to look at all the paths starting at the start state, ending at the start state, and following these directed edges. So can somebody tell me what will be the language of the words associated to this automaton? Yeah, exactly. In order to get back to the start state, now my path needs to be of even length, and all possible paths of length 2 are taken into account here. So the language will be indeed the set of all words of even length, including the trivial word, because I can just take the trivial path starting here and ending here, not using any edge. So epsilon will also be in the language. So the language of this automaton is the language, or is the set of all words of even length, of all words well over the alphabet 0, 1, including the empty word. Questions? Mm-hmm. Yes, yes, but epsilon is the empty word. So it's 0, 0, and epsilon does not read anything. So, yes. Yes, so a trivial path is also a path. More questions? Mm-hmm. Can you repeat the question? If some... So in this, I'm not sure if I understand the question well, but in this automaton, if there are some words which don't correspond to any path. So then this means if there is a word that cannot be read by any path, then this word is not in the language. But note that here you might have many paths corresponding to the same word. And if at least one of them ends in the accept state, then this word is in the language. Zero, zero, one is not in the language, because if I try to follow 0, 0, 0, 0, 1, 1 is in the language, yes. Because I go 0, 0, epsilon, 1, 1, epsilon. So this is in the language. More questions? Okay, so some languages are better than the other, and better are the ones that are languages of those automata, and these ones are called regular. So you will find in the literature 10 more definitions of the regular languages, but this is the one that would be useful for this course. So, definition, a language L inside the set of all words over some alphabet A is regular if it is a language, maybe the language of some of a finite state automaton over A. And now we need to specify some more notation for the words that we'll be using. So let W be a word over A. So now for any t, an integer, a non-negative integer, we denote by W of t, the prefix of length t. The prefix of W of length t, except that if t is longer than the length of W, then W of t will just be equal to W. So I'll write it here, length, which is the minimum of t. If t is too large, I just take the length of W. So it's the prefix of length t. If t is too large, then W of t is just W. So for example, I have a word 1, 0, 0. I take a prefix of length 2. This is 1, 0. If I take 1, 0, 0 prefix of length 3, this is just 1, 0, 0. And if I have 1, 0, 0 and look at the prefix of length 4, it's still 1, 0, 0. And for the final notation, here usually our alphabet will be the set of generators of a group. So it will be the union of S and S inverse for a generating set S of a group. Then or maybe and W is a word over A. Then by W bar, we denote the element of the group represented by this word. Then W bar denotes the group element represented by W. So W, V, U will usually mean words. W bar, V bar, U bar will mean appropriate group elements. And we will slowly now start talking about groups. And you've seen already Cayley graphs of groups. Let me quickly remind you what is the Cayley graph. So we will denote usually the Cayley graph by X. So let X be the Cayley graph of a group G with some finite generating set S. And remember, this means that we take a graph whose vertices are group elements, and we join two vertices by an edge, often a directed edge, if these two group elements differ by a generator from the right. And we label this edge often by the letter S, by the generator. So now let W and W prime be two words over this alphabet A, generators and their formal inverses. So let W prime be words over S union S inverse. And we say that these two words, W prime, fellow travel, maybe K fellow travel for some positive integer K. So we say that they K fellow travel if for all T, as before, non-negative integers, we have that these two prefixes, W of T and W prime of T, whenever we look at them in the group, then in the Cayley graph, they are supposed to be at distance at most K. Then we say that these words fellow travel. So in particular, W bar and W prime bar are at distance at most K, because we mentioned that if we take huge T, these prefixes are just W and W prime. And so by this definition, they are also supposed to be at distance K, but not only them, but also all these prefixes. Let me maybe make a figure illustrating this. So in the Cayley graph, I can look, say, at the identity vertex, and then I can start writing down the path labeled by my particular word W. So this is the bar is the element of the group represented by the word. I might have two different words representing the same element of the group, and I use the bar to say I'm speaking about the group element. So whenever I have some word W, I can look at the path in the Cayley graph, etc., labeled by W. So know that this is W1 bar, this is W2 bar, W3 bar, etc. The vertices through which I go are exactly these elements represented by these prefixes, and then I can look at W'1, W'2 bars in the Cayley graph, etc. And fellow travel means that this distance, this distance, this distance, etc., they are at most k in the Cayley graph. Questions? So not only W bar and W prime bar are close, but all the way when we trace out these paths, they are close along all their travel time. So that's why we say that they fellow travel. And now I can say what it means for a group to be biautomatic. Again, in the textbook, you will find plenty other definitions, but this is the one that's most often useful to work with. So the group G, as before, is biautomatic. If there is a regular language L over S union S inverse, where S is the generating set of the group, such that, first of all, when we look at the map from the language to the group, which assigns to each word the element that this word represents in the group, W bar is assigned to W. When you look at this map, you require that this map is surjective. So for every group element, there is a word in the language representing this group element. And there is a constant K such that two properties hold. So first of all, whenever we have two words in the language, for any W prime in the language that represent the same group element with W bar equal W prime bar, or maybe if they represent elements that are neighbors in the Cayley graph, or W bar is equal to W prime bar times a generator for some S in the generating set, we have that W and W prime fellow travel. So this is the first part of the definition. So words representing the same or close group elements, their corresponding paths stay close in the Cayley graph. So that's first part of the definition. And the second part corresponds to the similar picture as on the left board. So if we try to illustrate the first item on the left board, I would need to draw here these points either as equal or as differing by generator S. And now I need to draw the similar picture for the second item. So for the second item, I will have the picture where I have my identity and then I have one path, and then I have a second path, but starting at the neighbor of the identity. Now this path will be labeled by W, and this path will be labeled by W prime. So let me write, and I require them to be close. So let me write this in words, that for any, again, W prime in the language, with now W bar equal S on the left times W prime bar, we have that these two paths, so W and the word W and the word S, W prime, keep fellow travel. So again, these paths have to stay close at distance at most k in the Cayley graph. So whenever these two properties holds, the group is called biautomatic, and whenever only property 1 holds, the group is called automatic. So let me finish the definition by writing here. If 1 holds, but not necessarily 2, then the group is called automatic. And now we'll spend some time looking at an example, but if there are some questions, it's a good moment. If there is a language only satisfying 1, there is a language only satisfying 2. But you cannot, but it's an open question whether if a group is automatic, it's biautomatic. So it's an open question whether you can have, if you have 1, you can maybe change it a bit to simultaneously satisfy 1 and 2. More questions? Yeah, I will show you in a moment an example of a biautomatic group. Okay, so let's test this definition on the example I have in mind. So example is the group which is just the square of the integers. So it's generated by 2 elements, A and B, and there's one relation saying that they commute, AB is equal BA, and the generating set is the obvious one, consisting of A and B. So in the alphabet, A, we have 4 symbols, A, B, A inverse, B inverse. And it will be useful to us in a moment, so I will draw it already. The Cayley graph of this group. Well, let's have identity somewhere here. Then we have an edge labeled A joining identity to A, another edge joining it to B. Well, there is also an edge joining it to B inverse and A inverse. And then there is an edge joining A to AB and B to BA, but AB is equal to BA in this group. So we have a square in the Cayley graph. And if you work this out, you will get a whole grid of squares, which is X. So that's the Cayley graph of Z squared. And let's take the following language and prove that this language is regular and satisfies the biautomaticity definition. Namely, let's look at all the words of the form A to some power times B to some power, where K and M are integers. So there can be both positive and negative or 0. So note that with this language, not only the map from the language to the group is surjective, but actually it's a bijection. We can represent each element of this group by in exactly one way as A to the power K times B to the power M. So as a first exercise, let's try to prove that L is a regular language. So if K and M were non-negative, the automaton for L would be pretty simple. We could just first have a loop labeled by A, and this would allow us to take A to any power we want. Then we could move to another vertex, and then if we draw here a loop labeled by B, we would produce all the words of the form A to some positive power, label this epsilon, and B to some positive power. But unfortunately, there we have also negative powers, so we have to modify a bit this automaton. So we draw a separate start state, and depending on whether we will have positive or negative powers of A, we will either go here or to another state where we will loop on the letter A inverse. And then here we will also have another vertex where we will loop over B inverse. And then if we first go along a positive power of A, well, maybe then if we have a negative power of B, we have to go here. And similarly, we have to allow all those arrows that allow us to first take some positive or negative power of A and then some positive or negative power of B. So here we can take Y to be all states. So this is the finite state automaton whose language is exactly A to some power times B to some power. Questions? If I put the same loop here, then I would have words that have A inverse, and I would like really to have words where either there are only positive power of A or a negative power of A. More questions? Okay, so now we have the first board of the definition because we have a bijection between the language and the group, and we know that it's regular. And now we will prove the fellow traveler property. Maybe I should write that this 1 and 2 are also, as before, referred to the FTP, fellow traveler property. So we'll prove fellow traveler property with a very small constant. You will see in a moment what will be K. So I will erase already this board because we verified this part of definition. So now for the first part of the fellow traveler property. Well, let's see what paths our words take in the Cayley graph. Let's use the Cayley graph that we have here. For example, if we are going to this vertex, this is B times A squared, but in our language, we are supposed to go along A's first. So our path will first go along A, first go along A's, and then go along the B. So it will be A squared B. And if we want to go to this vertex, which is BA or AB, we'll also prefer to first go along A and then along B. So A squared B and AB. So this is in the example, but let's draw what happens in general. So in general, we will ignore this case because if we have two words representing the same group element, because our map is a bijection, is just the same word. So let's look at this case where they differ by a generator, and differing by B is a bit boring, so we'll just look at the case where the two group elements differ by an A. So let's look at the situation where we have two words such that W bar is equal to W prime bar times an A. And similarly as on the grid on the right, if this is identity, and this is my first word, some power of A, some power of B. If I take the word W prime, representing an element differing by A, then W prime will be here. W prime prior will be here, and the path in the language will just follow the same path until it reaches a point, a distance 1 from the end of the path labeled by A, and then it goes up a bit earlier. So notice that here these paths go together, and here they split, but they stay at distance 2. So here the distance is 2. And then if we go one step farther, they are still at distance 2, and so on till the end. So here, K, we can take 2. So W prime, W and W prime, 2 fellow travel. Okay, so this abelian group has a pretty small constant K. And the picture, yep. You're asking what happens when we have B here? You would like to take one of them to be B squared and another W B squared A squared. Well, then W prime is equal to, yes, this is not in the language, so I would have to be A squared B squared, and then W prime differs by A, so W prime would be A B squared. So this falls also in this picture. It's just that my picture is A squared B squared or A B squared. But still, this is the same figure. The picture for the second part is very similar. Now, the interesting case is when the generator is a B. So in the second case, let's look at the situation where W bar is equal to B times W prime bar. And again, then if W is this sort of form, then W prime labels a path here, and this is B. They differ by B, and again you see that consecutive vertices on these two paths. Well, these are not the same, but they differ only by 2, and we continue. At some point they even merge. So this is the same figure, but inverted. So as a conclusion, we know that this group Z square is biautomatic. So let me list.
Do we really have to check like W equals W bar equals W prime bar and W prime equals W prime bar A S separately?
So
for example, does
maybe if you're an abelian group, you can work your way to not consider all these cases, but in general, you need to consider all these pictures. So you need to look at this, because all these paths that correspond to our words are directed, and to check fellow travel property, you really have to consider the two cases. Either the two paths end at the same point, but they start at points at distance 1, or they start at the same point, and they end at the point that's the same or at distance 1. These are really two different cases. So let me list some examples of groups that are known to be biautomatic without proofs. Examples of biautomatic groups. So in the book,
The difference between L and G is that in L there is no cancellation. So if the relations.
yes, L is just a set of formal words. Yeah, so in theory, you could have in L words of form where you have A and A inverse. So Euclidean groups are examples. Here so Euclidean groups are the groups acting properly and co-compactly on the Euclidean space of some dimension. And you saw here one example of a Euclidean group being biautomatic. Hyperbolic groups. And you know that in hyperbolic groups, if you take all the geodesic paths, the shortest length paths, then you will have these thin bigons. But you are asking about this equality? It's just in the definition. So this is in the group. This is an equation in the group. So in the definition, we always, in part 1, we put always a letter on the right. But so this is the main point of the definition. You have two paths. You know they differ just by one, but on the right in the Cayley graph. But you would like these paths to have something in common. And from the definition of the language, it's not obvious that they will have something on the common because, as you said, A's are supposed to be in the language on the left. So it's a lucky coincidence that here we have fellow traveler property. So that's a property that's really, in general, hard to verify. So for hyperbolic groups, you need this fellow traveler property. It's not so hard if you just look at the paths labeling, words labeling shortest paths. But you have to check that the set of words labeling shortest paths is a regular language. And for that, you need finiteness of cone types, etc. So it's some work to prove that hyperbolic groups are biautomatic. Cat0 cubical groups. So groups acting properly and co-compactly on Cat0 cube complexes. This was proved by Niblo and Reeves for free actions and generalized by Świątkowski to proper actions. And maybe I'll say some words about the paths that one needs to use here later on. They did the free case. They did the free action. Free and co-compact. And here proper and co-compact. It's definitely not known, but maybe it's false. I'm not sure. I would have to think about an example, but likely it's not known. If just proper action is sufficient. Systolic groups, if somebody knows what these are. So these are groups acting on not now cubical, but simplicial complexes of some combinatorial non-positive curvature. And Heli groups, if you've heard about them, there are many classes. But Coxeter groups, even though there are means of forcing a Coxeter group to act on a cat-zero cube complex, the action is often not co-compact, so you cannot apply this cubulation trick to prove that Coxeter groups are biautomatic. And for the last part of today's class, I will try to motivate a bit this definition of biautomatic groups. So what are the maybe most common properties of automatic or biautomatic groups? So one thing you can do with these groups is you can solve the word problem. So there is an algorithm given a word over the generating set to decide whether this word represents a trivial element or not in the group. And also, in the case of biautomatic groups, a conjugacy problem, the word problem and conjugacy problem are solvable. Conjugacy problem is the problem that now takes as input two words and is supposed to check whether these words represent conjugate elements. But the thing I will show today is something that will show you that the word problem is actually solved in a very effective way. So I will show you that biautomatic groups, even just automatic groups, have a quadratic isoperimetric inequality. Mm-hmm. Yes, it's an exercise that the group is biautomatic with respect to one set, it's biautomatic with respect to the other, but it would probably take us another half an hour to do it. So, yes. And really effectively. Okay, so let me discuss a bit now this isoperimetric inequality, but before doing it, I will say it again. It's not invariant under quasi-isometry. It's just invariant under changing the generating set. Okay, let me write a lemma that will help us show different properties of automatic groups. So let G be an automatic group. So remember just part one of the definition. And say that the language from the definition is, as usual, called L. Then there is a constant n such that if we have a word W in the language and the group element G of G is a distance 1 from W bar in the K-ray graph, then G has a reasonably short representative in the language. Then G has a representative of length at most the length of W plus this constant n in L. Because if we are looking for a word not necessarily in the language, well, then they differ by 1 in the K-ray graph. So we would have an element representing a word representing this element of length W plus 1, but we want a word in the language. And it turns out that the cost will be also bounded, but not necessarily 1, maybe some n. Let me draw a corollary from that before we prove the lemma. So a corollary, that's our motivation for the lemma here, is that any element of the group G represented by a word W over the generators, but not necessarily in the language, can be represented in the language can be now represented by a better word, by a word in L of length that's not so bad, at most n times the length of the original word plus some constant, n0. And in fact, I can tell you what this constant n0 is. Where n0 is the length of maybe a representative of identity in L. Because see here, epsilon might not be necessarily in the language. So, but since the map from the language to the group is surjective, even if epsilon is not in the language, there is some other word representing identity, and we just define n0 to be the length of some word representing the identity. And the corollary says that now if we want to represent any group element by some word in the language, then the cost is this n0 plus this constant n times the length of the original word, which might not be in the language. So there is this multiplicative and additive constants that after we add them, we can change a word not in the language representing an element in the group by a word that's already in the language. And I think you can see how this corollary follows from the lemma. If we just take W representing the trivial word, so say if you just take W equal to epsilon, well, this is 0, and we use the definition of n0. And if W has, and then we prove this by induction, adding one letter to W is exactly applying the lemma. If we can represent some prefix of W by the word of length n times the length of the prefix plus n0, and we add one more letter, look at another prefix, we are exactly in the setup of the lemma where we have to add an n, and this adds another term in the inequality. So to prove this corollary, to efficiently represent these group elements, we need to prove the lemma. Okay, so let's try to do it. Proof of lemma. So we will take a rather huge n. So let n be equal to the product of two numbers. First is the number of states of the automaton gamma with language L. So that's the first term of the product. And the second term of the product is the number of vertices in the ball, let's call it Vk, in the Cayley graph X of radius k around any vertex. So if we take any vertex in the K graph, look at the ball of radius k, where each edge has length 1, then we have some number of vertices there, and we take the product of these numbers, and this will be our n. And let's try to prove that the lemma holds with this particular n. Okay, so let's recall the statement of the lemma. We have identity here. We have the path labeled by the word w. And now we have this element g at distance 1 from w bar in the K graph. And we will look at the ball centered at w bar. So this is our ball bk. It will be centered at w bar. So now we would like to prove that g can be represented by the word that's not too long. So let's take the shortest word representing g and prove that it's not too long. So what would happen if it's, so let v be the shortest representative of g, and say it's long. So what happens if this word v is long of g in the language? We would like to prove that the length of v is at most the length of w, and remember that w belongs to L, plus this constant n. So if the length of v is greater than the length of w plus n, we'll try to reach a contradiction. We'll try to reach a contradiction with the minimality of the length of v. Then we will apply the fellow traveler property to the times t that are greater than the length of w. And remember, if we take the prefix that's larger than the length of a word, and then we just look at the word itself. So there are plenty of these prefixes v of t, where t is larger than the length of w, and this means that all these distances are smaller than k. So I was right to draw this last part of the blue path inside the ball. Because by fellow traveler property, once t is large, this entire path sits in the ball around w bar. By applying the fellow traveling property, we have that all prefixes, in the sense that we take the vt and then see what happens in the group where t is equal, say, w plus 1, etc., w plus n plus 1, lie in the ball of radius k centered at w bar. So there are really many of them. There are more than n, and n was a huge number. So now we use the pigeonhole principle to say that there are some two t's for which something coincides, thus, or some t1, t2 as above, we have that these two vertices, this one and this one, are the same. So I'll correct the picture to draw the fact that this path goes 2 times through the same vertex. This is v t1 equal bar, equal V of T2 bar. But to have that these two vertices are equal, I will just need the second part of the definition of n. And now the first part guarantees that not only these two vertices are equal, but the path, which is labeled by these prefixes in the automaton, also ends at the same vertex. So remember when we have this blue path in the K-ray graph, since this path is a word, it's labeled by a word in the language, we have a corresponding path in the automaton. So in the automaton gamma, we have here somewhere the start state. We have our path labeled by V in the automaton, and since the number of the states in the automaton is also small, at the time T1 and T2, we also visit the same vertex in the automaton. So end the path in gamma labeled by V of T1 and V of T2 ends in the same state so not only we have the loop in the K-ray graph, but also we have a loop in the automaton. And then the trick is to cut out this loop in the automaton. We started here at the start state, visited a vertex twice, ended in an accept state. So this path, after removing the loop, this path is still in the language. It's still a directed path in the automaton, starting in the start state and finishing in the accept state. But cutting out this path in the automaton, since these were the same elements in the group, boils down to also cutting the same path out in the K-ray graph. And then we have a shorter word representing the same element G, and we get contradiction with minimality. Yes, but we assumed that n is equal to the product. So there are really not so many vertices in the ball. So eliminating this loop, contradicts the assumption on the minimality of the length of W. So this finishes the proof of the lemma. We had some way of representing W in the language. We want to represent G in the language. If the length of the shortest representative is too long, then it travels twice through the same point, both in the automaton and in the graph. And after cutting out this loop in the automaton, we get a word representing the same group element that's shorter. So this proves the lemma and consequently proves the corollary. So we have an efficient way of representing words in our language. Mm-hmm. So if we have many times, the number of times is for which our vertices on the blue path lie in this ball. So we have many V bars in the ball. And so this means that there are at least two of them that that are the same in the ball, and simultaneously, because we took this n really large, these vertices come from the states that are also the same in the automaton, because n is the product of the size of the automaton and the size of the ball. So you take more than, if we have a rectangle of sizes say k and l, if we take more than k plus l points, then we have we have 2 points that are the same in the rectangle. They are both the same first coordinate and the second coordinate. Okay, I will state now the theorem that I will prove next time. Which is the point of the lemma, that every automatic group G, first of all, is finitely presented. We didn't know this so far, but we'll prove that it's finitely presented. So it has the form not only it has a finite set of generators, but the number of relators can be made finite. What's it? Yes, we assume it's finitely generated, but now we'll prove that it's finitely presented. So G is equal to, it's presented by a set of relators R with R finite. And moreover, satisfies what's called the quadratic isoperimetric inequality. And what does this mean, this quadratic isoperimetric inequality? This means that there is a constant let's call this one C, such that for any word, say W over our alphabet S union S inverse, that represents the trivial element such that W bar is equal to identity, we have that this word is equal to the product, and this is inside the free group generated by S. This word is equal to the product of the conjugates of relators. So we take the relators Ri in the relator set, and now we conjugate these relators by Gi, where Gi are any elements of the free group. But if I just write that, this is just the definition of being presented by the set R. Being presented in the set by the set R means that every trivial element is exactly the product of conjugates of relators. But now I want the number of terms in this product to be small. I want the number of terms to be n, where n is bounded by the length of W squared times some constant. So pictorially, I will end by illustrating this definition on the example of Z squared. So let's look in Z squared at the word W equal to A squared B A minus 2 B minus 1. So this is this word in Z squared. So you can draw this word. This is a word representing the trivial element, but you can decompose it as this balloon here. times this square. So you can write this word as this balloon is a conjugate of the relator. So it's, I can write it as A, because this it is labeled by A, and then A, B, A inverse, B inverse. Now go back here, A inverse. And this blue loop, A, B, A inverse, B inverse. So you see this is the product of two conjugates of relators. And in the diagram, you somehow see this word being filled by a diagram with two squares. So the number of terms in this product is the number of relators needed geometrically to fill the loop. This is why this word isoperimetric inequality is used in the definition. So next time, we'll prove this theorem. Thank you.
Questions?
In your in this proof here, this is DFT. They're allowed to not end at an accept state.
Yes, yes. This state might not be an accept state. But this one is an accept state, and since they are the same, you can just forget about this part.
But we can still speak of DFT bar.
Yes, because we can just see what this element labeled by V represents in the group.
Right. So DFT need not be the language, but DFT bar is still an element of the group.
Yes. I don't know if it's known. Somebody knows? No, if it's biautomatic, then the conjugate problem is solvable, but I don't know if there is an example of an automatic group without solvable conjugacy problem.
So what about relatively hyperbolic groups?
Say it again?
Relatively hyperbolic groups.
It depends on whether the groups you are relative to are biautomatic. I think if the groups you're relative to are, I'm not sure, biautomatic or automatic, then the ambient group is also. There was a question? It's not known. It's not known.
Are there any like nice combination theorems to these, like the direct product of two automatic groups?
Yeah, I would imagine that such easy combination theorems, yes. But if you start amalgamating over something weird, then I don't know. Yes, so I will not do this during this course, but using the lemma I just erased, you can really solve the word problem in effective time, quadratic time in some sense.
Can you give an example of a group with quadratic isoperimetric inequality but not automatic?
I think some Heisenberg groups would higher Heisenberg groups would have quadratic isoperimetric inequality, but it wouldn't be automatic.
When you say one can solve the word problem or quantity problem for biautomatic groups, is the automaton like part of the input, or is it just the presentation that's part of the input and like the algorithm finds an automaton?
Yeah, I am not sure even if there is a constructive procedure. So when I would have to think about it. But see, when we write that the word problem is solvable, then we say there exists an algorithm. But I'm not 100% sure there is a constructive way to pass from this automaton and appropriate automata corresponding to the fellow traveler property to the algorithm solving the word problem. I'm not 100% sure. Mm-hmm. Yes, I will build the automaton in the last class. Is it? I think it's unparameterized. And for hyperbolic, yeah, I think. I mean, if, okay, I'm not 100% sure if you have weird groups, it will be a quasi-geodesic. We should look in the textbook. We are slowly entering the grounds that I am not an expert in. You will see that I know a lot about Coxeter groups, but from here I will mostly just draw the definition, and the intuition we'll have from these examples, and then we will dive next time into Coxeter group world.